Science you can try at home. Hi guys, in this next experiment we're going to need a few very simple things. Now I'm sorry my camera's struggling to adjust for focus there, but all we need is a little jar of water and a very small needle. Now the question is, can we make this needle float on the water? Now naturally you'll say, well no. Needles are made of metal. In fact, if I pop that straight in the water now, it'll sink. Bloop, straight away. No hesitation, just sinks. Is it possible to make it float? Well, here's a theory. There's something in science they call surface tension. Just draw off our needle. And it's possible for very light things that are normally heavier or more dense than water to sit on top of the water. It's not exactly floating, it's a different thing. And we're going to try that today. So what we'll do is we'll very carefully first, might just see if we can split our bit of paper. We want only the tiniest bit of paper. And now this does require patience, guys. We're going to pop that on there. No, it's sunk straight away. And we're going to use that. No, we might need another bit after all. Put that on there, and we'll put the needle on top. No, okay. Does require patience. It'll take a few turns. Success! Success! We've got some success. The needle is floating on there, and turns out that the tissue trick didn't work particularly well. But that needle, you can see, I'll see if I can bring it in closer for you, is sitting nicely on the surface. Now, what you might notice when we get in real close is that it's kind of dented into the water. It's not exactly floating. There's a wee bit of oil on there, but it is dented into the surface. There's almost like a skin of water that it's sitting on. Now my question is, can we influence it? So what I have here is a magnet. You might be able to see it just in the corner there. Now I'm a long way away from the needle, but I can make it move around. And now I'll zoom out a bit again. You'll see my messy table, but you get the idea. Magnet's a long way away, but it's still able to influence what that needle's doing. What you may also notice that is when I leave it, I haven't used the magnet on it in a wee while, it's settled down into the same position that it started. It's pretty much in the middle of the bowl and it's pointing in a certain direction. Now, you won't be able to tell from here in the video, but it's actually pointing north. What it's done is it's created itself as a little compass. So that direction that it's pointing in is north is that way, south is that way. It's a little trick in the bush that people can use. If you've got a magnetized needle, you can float it in a little pond of water, just using that surface tension trick, and it'll point to north for you, so long as it's even slightly magnetic. How interesting is that? So, how does surface tension work? Why can water support something very light on its surface, even though the thing that's on it is slightly heavier than the water? Well, something very interesting is happening between the layer, the top surface of the water and the water that's underneath. Might be water, might be some other liquid. Water is a good example though, because it has quite a strong surface tension. So what's happening? Well, imagine, if you will, if you could go right down into the water and see at a microscopic level. And these chocolate buttons that I've got here represent the molecules that are in the water. Between each of these molecules that are moving about all of the time, there are forces pulling and pushing against each other. And they keep moving, and that's the way liquid behaves. You've seen it's quite mobile. It pours, and under the surface of the water, the forces on each of these are relatively equal. They're drawn together and they push apart and they move and they wiggle all around the place. That's happening all around. So each one of these molecules is having is round about equal amount of force pushing it in and out and around, and so they generally sort of operate in the same sort of way. So what's different about the surface? Well, we'll have a look at that in a second. You can see here I've rearranged a few of these so that there's like a line where the surface of the water would be. So underneath here is the liquid water, above it would be the air. Now something interesting happens where the water stops. So where each of these ones under the surface are being equally pulled around, up, down, sideways, backwards and forwards, the ones at the surface are mainly being pulled down. So there is this tension here and this tension here. There's a little bit of sideways, but there's very little force pushing them up. And in fact, gravity plus all of the other attractive forces underneath are pushing it down. And what happens gradually, well, probably quite quickly actually when I think about it, is that these molecules at the top here kind of squash together because they're primarily pushed down, and it makes a very thin layer of water molecules or liquid molecules at the top that are more close together. These other molecules down here are also sort of pushing it up, so that those that line of molecules at the top gradually coming down don't keep going down. They're supported by the other molecules that don't like to be squashed up. Water molecules generally don't like to be squashed up, so the only place that it really compresses is right on that surface layer, and it's very thin and very weak. You can easily pop your finger through it, obviously, but it's strong enough to hold up something very light. Now it's quite stretchy, this skin. This is the interesting part of it. If we were to put something here, some kind of weight, it would stretch out. I'll just pause this here and I'll rearrange my chocolate buttons. So imagine this Connects wheel here is an end-on view of a needle or the foot of an insect that can walk on the water, for example, like they're called waders, aren't they, I think? We'll have to look them up later. So what's happening there, this thing weighs more than the water, it has higher density than the water, so it wants to go through, it wants to sink. Gravity's pushing it down, same with the foot of the water strider. But there is surface tension here that's quite stretchy, and because this needle is so light and its weight is spread out over quite a big surface area compared to its weight, the surface tension is strong enough. You can see it stretches a bit, and you'll see that in the video that we had previously. Water stretches and makes a little indent, and you can see that quite clearly. If I was to press it, it would break through that and sink just like normal. This would heal itself up and come back up to normal, and the metal thing would continue on sinking. But if I am very careful with my needle or whatever light thing it is that I'm putting on there, it will just sit on the surface. Now I have to be careful not to put it end on, because the pressure at one end is enough to break through the surface of this skin. Now, you could experiment. You could say, what is the biggest needle I could float, or I could rest on that surface? And that's what you could do at home. You can have a try. See what you can get to sit on the surface. The other place you might see surface tension in action is droplets on the surface of a newly waxed car, freshly waxed car. The water is, what they call it, is beading. It beads on there. It makes these lovely dome shape circles of water. And it's surface tension that keeps those domes in shape. And they're actually surprisingly tough. So our next experiment could be to see what we can do with beads of water on a surface. The other thing you could look at, if you're really, really quick, is a droplet. A droplet of water also has surface tension. In fact, because of the forces that we talked about earlier, if you let the droplet go, gravity has little effect on it, because it falls pretty quickly at the speed where gravity doesn't matter to it so much, and it will naturally try to form a sphere. And that's why the droplet that eventually lands on the bonnet of the waxed car, for example, will make a circular blob, and that it'll dome over the top. In the meantime, as it's falling through the air, the water will also form little spheres. Now, we often get told that raindrops look like this. They're a teardrop kind of shape. That's just storybooks. That people kind of imagine they look like that, because when they hit the window and start running down the window, they actually do form that sort of teardrop shape as they're dribbling down the window. But in reality, each raindrop, each drop of water, is roughly spherical. Now it wobbles around a little bit because of the wind hitting it and that sort of thing. You can see here on the roof of the car here, this is Edmund the Mini. I've waxed it before, precisely for the purpose so that the water won't stick to it. The wax is what they call hydrophobic. It doesn't like water and it repels it, which is ideal for an old car because you don't want the water to stick around. The interesting things about this is how it beads. You can clearly see the surface tension holding them into roughly round type of shapes. Now the smaller ones tend to be more round. The bigger ones get a little bit more out of control. And we can still even touch these, and the surface tension is so strong, you can see it peeling up. It sticks to my finger a little bit there. I'll see if I can make that focus a bit better. It'll stick to my finger a little bit, you can see that. And you can even merge these bubbles, these little pools of water, or stretch them from one to the other. And the surface tension will keep that shape that you've got there. Or I can make my own new one. So the surface tension is weak compared to your finger, but it's strong compared to the water. So it holds together in these sort of little bubbles. Fascinating, really. Let's have a bit more of a play with the idea. So I've set up some lovely tin foil here, and I'm going to drop some just tiny droplets of coloured water on there. They don't have to be very big. I'll see if I can get them a wee bit bigger there. And you can see that they've formed beautiful droplets, each encapsulated, enclosed in that lovely little bubble of surface tension that keeps in there. What I want you to try is to see if you can move the beads around on the shiny surface. You could also use wax paper. I didn't have any wax paper at my house, so I've just got this tin foil instead, which also works really well. Okay, so let's see if we can move an entire bead across to another. Just kind of pick it up with this here. No, don't want to, oh, that little one moved. See how it merged into that one? We'll come in a wee bit closer so you can see what's going on there. See if we can get this one to move across to its buddy. Ooh. You can even mix the colours if you're really careful. There's not much blue there, so it's going to still mainly red. Let's see if we can pull it across. We've made a much larger blob. That's a mixture of blue and red. We've got a kind of almost purple one there. Let's see if we can get this one across too. It's a little bit tricky. A little bit of fun though. You can try this at home. The question is there a way to break the surface tension? Can we do something that breaks that little bubble, that skin? Well, yes, there is. Now, lately we've been learning a lot about soap and hand washing and things like that. Well, turns out soap is a kind of substance that breaks down the surface tension of water in particular. So what I've done here is I've taken this end of the skewer, and it's just got a tiny bit of soap on the end. It's just Sunlight dishwashing soap. Let's see what happens to the bubble if I just touch it with this. It's popped it, it's gone flat. Let's try this bigger one. Works on some and not on others. There we go. Look at that. Goes flat. It's like takes all the strength out of the surface tension there. Starts to flatten out, you see. And that's what soap does. It helps to disperse the water and takes away the dirt at the same time. Here's another surface tension experiment you can try at home. This one's really easy and you've probably seen it on the internet before. All you need to start with is some black pepper. It's very light and floats well. Some water, a nice clean dish, doesn't have to be any particular kind, and some soap. Could be this dishwashing soap, or it could be just regular soap that you wash your hands with. Let's see how it works. First of all, just pour in very carefully so don't splash too much. Bit of water, fill it up. Then, with a similar sort of care, shake the pepper onto the top, and hopefully you'll see that that gets a nice even coating of the black pepper on there. You can see that nicely. For the next bit, I'll probably zoom in a wee bit. You can see the water's still swirling around. Here's the fun bit. We've got the black pepper sitting on top of the water. The surface tension is keeping it on top of the water there. It is also, I suspect pepper would float anyway, it's pretty light stuff. But in this case, it's not even sinking into the water at all. Now, on the end of my finger, I've just put the slightest dab of soap. Watch what happens closely. If I put my finger straight in the middle of this, it's something I can easily try at home. Watching. Boom. Instantly, it spreads out. What's happened? We've broken the surface tension and the water has split apart basically and taken the pepper that's sitting on the surface with it. You can see it slowly starting to creep back in. We'll see if we can do it again. So it's come back in about as far as it's going to. Let's see if we can make it zoom out again. A little bit. What happens if I touch it on the edge? Goes out like a rock in a pond, a concentric circle from there. Notice that the pepper actually does sink. It must be more dense than the water. So once the surface tension is broken, it pops down below. You can see the little grains of pepper have actually sunk. How interesting. So the next thing, guys, is to have a go for yourself. Always ask permission to use things like pepper and soap. They are valuable things. Experiment, have fun, see what happens. One last try with this big bubble. Just going to drop a little bit of red in there